Vale. Vale. Ponte ahí. Vale. Okay. So, hello everybody. Thanks to come here. Today I will make a brief introduction of formal methods, testing and debugging. That is the part that I was working with Tecnalia the last weeks. First of all, like it's a software engineer stuff, I will start to explain a little bit what is formal methods, why we need it. When you start to work with big systems, with big program systems, and it's not like we work with, it's not the same process that we make when we are working with when we are coding. The software development is making a lot of stuff, and there are a lot of groups. The first group make the architecture, they think how to make everything, and they design the code. There is another part, is the code generation, that another group start to make the code and write the code and everything. And then there's another part that is the testing and the testing, that what they make and they ensure is that check that everything works okay and there is not bugs in the code, and they can put the code in an industrial application or somewhere that they want. So we are going to focus in the software quality control, that is testing, and the testing is the discipline that they try to ensure that everything works okay and there are no bugs in the system. And why we need they distinguish between two steps. The first thing is verification, that they test that everything works like it has to work, so the program works. And the second part is validation, that what they make is that everything works and only works for they plan to work, because maybe you make a very good program, but if there are some bugs and then some hackers can use these hacks to destroy your code and destroy your system, so you cannot police it. So why is necessary software checking? Some studies say that that not check everything okay, not check the system, can cost more than $10 billion per year to the industry and to the company. So for the companies, a very hot spot, a hot topic, and they need to focus a lot in the testing. And for example, one example of bad code tester is the Iron 5 crash, that they don't check everything, that's the software of the engine of the rocket, and when they launch the rocket, it explodes for a software fail. Yeah. So what methods they use to test, to check that everything works okay? They use the software testing and the formal methods. So right now, we are going, because when I start to make this, you are going to think, why we need software testing if the code that we developed right now and the algorithms are short and you can check it by eye? It's because right now the hardware is growing up really fast and the algorithms are growing up really fast. And finally, in a few years, in 3-4 years, the code are going to be on you cannot check everything by eye, and some methods are some classical methods have to you have to make some methods to check everything. Why also is really necessary to adapt the quantum software testing and the formal methods to the quantum stuff is because quantum nature is not intuitive. And finally, when everything's grow up, a lot of engineers are going to start to working with software, quantum software, and they don't know as much as mathematical and physics like right now the code developers. So they are going to make a lot of mistakes, and everything have to check. You have to check everything. And finally, because if you want to put quantum software in some industrial application like robots, you have to be sure that this is not going to fail, because right now you use it in the computer, but if you are going to put it in a rocket, you have to check that everything works okay. So first, we are going to speak about software testing. Software testing is a really easy discipline. It's a really simple method that what they make is basically they put a lot of inputs in the program. they put inputs that is outside of the boundaries of the program, inputs that are wrong, inputs that are okay, that you know the result and everything, and then check that everything works like it has to work. There are a lot of methods, for example, fast testing, functional testing models, quantum mutation testing. There are a lot of methods, but basically what they say is to play with the code, play with the inputs, and see if it works. Because, for example, if you put an input that is outside of the boundaries of the system, it has to fail. It don't have to make anything. But what is the problem of the quantum software, of the software testing? That the software testing is based on measurements, to make a lot of measurements and check everything. And we know that in the quantum systems, if you make a measurement, you destroy the system, and the measurements are also probabilistic. So it can be that you make the measurement, it's not the result that you want, but not because it's not because the program fails, it's because it's a probabilistic measurement and it can fail. So in the other part, there is the formal methods. The formal methods change this mind. It doesn't work with the inputs, outputs, and what they say is describe the program using mathematical and logic procurement. And yeah, normally it's not normal to be used in the classical world because because you need a really specialized workers and you have to check everything mathematically. It's cost more money for the industry, and testing works okay for the classical world, so they don't use it. But right now here in the quantum world, that you are not going to be able to make everything with measurements, can be very useful. And here I present three methods that can be interesting for formal methods and can be adapted to quantum formal methods. And let's be focused in each method to see how it can be used. The first one is the ZX calculus. It's a graphical language. What they make is they take the circuit, the normal circuit, and then they decompose using a diagram language. It's really easy and it's made with dozens of colors, and finally and then you have some rules. The rules are very simple. They are color changing, spider function, identity removal, a little bit more. And what they make is to simplify the circuit. For example, here we have a Hadamard with a control gate, and with the change color, they can change this, and finally you arrive to this one. This is the diagrammic expression for the Hadamard CDNOT gate. So it can be useful for two things. First, it's useful for optimize the circuit. And then also, if you have a really complex circuit with a lot of gates, finally you can arrive to the final circuit, to the more simplified circuit, and see if the system works like you want to work. The second method can be the path integral. The path integral, what they is based in the Feynman idea of path integral, and what they say is to write the circuits using exponential sums of exponential. They rewrite the system using this expression where x are the inputs, p x y are the phase, and phi x y are the output. So, for example, you can rewrite the Hadamard gate using this expression when you have here the path integral, you have here the output, and you have here the input. And why it's interesting to change the nomenclature from the circuit, from the matrix to the path integral, is because with sums of exponential is really easy to implement in a computer, and that the computer make alone and calculate everything, simplify everything and optimize a lot the system. And for example, here I saw an example that is a really simple example. Is apply 2 times the Hadamard gate to a circuit X. You input the X, and when you apply, you take the other expression of the Hadamard, you write it 2 times here, and then you can simplify the I1, getting this result, and then it's like mathematical stuff that you playing with the numbers, and you finally arrive to this expression. It's really easy to make. And you arrive that with 2 Hadamard gates, you arrive to the unitary gate. So with the path integral, you can simplify, optimize, and also you can check that everything works. Okay, for example, you have a Toffoli gate in Clifford T algebra. there are a lot of gates. So finally, you can achieve to the final expression and see if everything works right or not. No, because they make like they make sums. It's based in path. The idea is path integral, and what they say is they can put a lot of in paths. Like for example, for a circuit, you can make a lot. This is a Boolean function, so you can prove with a lot of functions, and so the functions have like a weight, and you can optimize and see if this is the best option or it works like it has to work or not. Um, yeah. Okay. And finally, I want to speak about the Hara-Floyd logic. The Hara-Floyd logic are really common in the classic world. And what they make is they write the program with triplets. The triplets are formed from the P, the C, and the Q. The P are the precondition, are the inputs you are going to put in the compiler. The C are the real program, and the Q are the postcondition. So what you make is using the axioms and the logic steps of the Hara logic to see if the range of the program works like you want to work. For some, normally they choose. They have here, for example, here. They have here the compiler. This is the program that you are making, and this is the output you want to reach. So using the action of assignment, you can see what are the preconditions that you can have to put to get this post condition with the program. Okay, they are all a logic preservement. And then working in the post condition and storing in the precondition, you can make much more general the program, and you can see the limits of the program and where are the range where it has to work. And how can you adapt the Hara-Floyd logic to the quantum world? Well, what they make is they introduce the ghost variables. The ghost variables are something that is not in the triplet. They are not work in the logic, but there are some condition, the boundary condition that you have to put in the system, but for everything works right. And for example, are non-local variables like entanglement, probabilistic measurement. You can put here the condition that the system that you are making wants to achieve. And then this normally is making in normal algebra spaces, but you can adapt it for the Hilbert spaces, and everything works the same that when you are making for classical devices. Okay. So the idea here is to see what I'm doing and what I will do. The first thing I'm making now is the state of the art of validation verification, because it's a newborn discipline here, because right now all the codes are very simple and nobody start to look it. So I want to get all these methods and see how they work and study them. Then I'm developing with an algorithm for the Epicus project. So what I want to do is to apply these methods and check see how they work and see what can be improved in these methods and go deeper in them. And then these methods are really simple, and if you make very big programs, they are not going to work. So they are done. There are a lot of classical formal methods that are really useful in the classical world. So the idea is to try to adapt them to the quantum world and see how can adapt them. And another very interesting thing is that is really important in the quantum stuff is the loops. Like all the programs work with loops, with while and with for loops. And right now, when you are working with the quantum, when you are working, and you have to check if it stops when it has to stop, or it stopped before or later. And right now that you have to make the measurement in the loop each time to study them and how to check if everything works right or not is a very hot topic also for the software engineers. So the other idea is to develop formal methods to check if everything works for formal loops or not. And finally, this is what I'm doing these days. Is the state of the art of formal methods. My idea is develop a little bit more these programs and apply it, for example, for the IBM or wherever I have to apply it.
that's similar to the path integral and stuff. Can you use it to optimize it with the way that we were talking the other day, like reduce the number of gates or something like that?
Yeah, they use it. This thesis, this postdoc thesis, and what they make is to check Clifford T algebras and how it can be optimized and everything. I think it's not very developed, this method, because it only works for Clifford T, and they use it more. Normally, they use it to check if the program works or not. They put the path, they make the everything. They put the circuit that they design, and finally, with a software, you can arrive to the final state and see if it works like it has to work. But yeah, probably if you adapt it, you can make optimization methods and check, because they also try to optimize the Toffoli gate in the Clifford T algebra, and they achieve a good result and reduce a lot the Toffoli gate and achieve to the best for a number of gates. So yeah, probably yes.
It's applied to these problems when they are classically efficient simulated.
Yeah, they make it for classic. Yeah, it's why they choose the Clifford T algebra, because it can be really easy to implement in a software, in a normal classical software.
Because the logarithmic time, if you start with in the computational basis and you measure in the computational basis and you use only Clifford gates.
Yeah, but with this one, the interesting is that they achieve really good results. They can with this expression, and automatically the software, because they prove with a lot of, they make a Boolean function and they prove all the coefficients, and they can choose 4,562 possibilities and check and try the best one automatically in 30 minutes. Like you can choose, they can make what you want in 30 minutes. You can choose the best one.
Yeah, but this is because what they are doing. So there is a theorem, classical theorem in quantum computing that tells you that tells you that every circuit that uses only Clifford gates and the initial states in the computational basis, and you measure also in the computational basis, then you can do it. This can be simulated in logarithmic time.
Yeah.
So this is the reason why they can go to 100 qubits
Yeah. Yeah, they say they because everything they have 5-6 papers for path integral, because they don't make a lot. They say they want to apply it because they start with Clifford because the easiest to program and everything. But yeah, the idea is to adapt it to more complex systems and see if it works or not.
Can you explain a little bit more the previous one, the set X, because it was, for me, it was like magic.
Okay, what they say is like it was proposed by Cook, I think, in the Dodo book. What they make is that you can draw all the circuits. Like they say that these circuits, these diagrams, or the matrix are really complex for the human being to understand and to simplify. So what they develop is like Feynman. They develop diagrams to write everything, and with a very simple rules. Because, for example, you can move a Hadamard if you have here a vertex that the reds are for 0 and the green are for 1 here. So if you have a vertex, you have here Hadamard, you can make here a 0. You can make you change. Obviously, you have here a 0. You have here the Hadamard that you make the compose system, so it changes to the red. And then you can these ones you can put it together, because with the spider rule you can put two gates of the same color. You can add it together, and finally you can. It's a method to simplify, but to be more visual, to make more visual the circuit and simplify everything easily. And there are a lot of papers to start to work with the set X diagrams, and it looks like it works really good.
I understand now when you told that the 0 is the green and the red is the 1. For me, before it was really.
Yeah. There's like is this there are a lot of they propose with red and green. But there are a lot of semantics. When you read the paper, you have to check if they use these diagrams. All the rules are the same. Like when you are reading a quantum field theory, they change the nomenclature every time you read a new book. But yes, the Cook, they say this is the Cook expression. That's the first one.
Can you apply just that to test that if a circuit works as intended? Can you use just simply the fidelity of the quantum circuit compared to the ideal thing that you want?
Yeah, but the thing for testing is that, because when I explain validation and verification, that not everything has to, because if you measurement the fidelity, you know that it works, but you don't know it works when it don't have to work. For example, if you want to something work when in a range of 0 and 1, you have a range of 0 and 1, you have this range of temperatures, it has to work, and you have, for example, you have a program that you have a room temperature, and from 0 to 1 it gives you a number, I don't know, some output. You can test this one and it works for this stuff, it's okay, but you have to know if it works for some random stuff, for example from 2000 degrees. You have to, the program has to fail because maybe you want another output. Or the thing is that if you measure all the fidelity, you are in the range that you are comfortable, that you only know that it works, but you don't know if it works when it don't have to work. The testing is more basic, that to check all the points, boundary points, and check if everything works or not. It's important that it fails when it has to fail also.
Yeah, I was thinking about not the fidelity, the usual one that you have an input and you know the output and then compare the fidelity, but the gate fidelity.
Yeah.
Like take the circuit as a gate and see the fidelity that for that you have to check every possible input state and select the worst fidelity of the model and then assign it to the circuit. It's like this quantum control, but brute forcing the process.
Yeah, there are. Yeah.
Probably it's not the optimal way.
Yeah, the thing is that to find because right now with simple cases it's really easy to make everything by eye. But if you want to scale it, you have to adapt it everything for a complex system.
Anything else? No? So we jump into the papers.
Okay.